Hello dear students, in this session let us start with a new topic, that is number theory. Number theory is nothing but study of properties of numbers. So if you are studying the properties of numbers means it is nothing but number theory. Okay, here in cryptography if I say number means it is about integers. Specifically, we are more concerned with positive integers. Okay, so we give more prominent to study the number theory for two reasons. One is it has historic significances. This is one of the reason. And another reason is integers, that is more specifically your positive integers, are building blocks of your real number system. These are building blocks of real number system. For these two reasons, studying number 3 plays a prominent role. Okay, so now let's start with the actual syllabus, that is divisibility. So how can you define your divisibility? In order to define divisibility, first we have to consider two positive integers, right? This is very basic thing which you have already studied in your basic classes. So two positive integers, say a and b. Now I have to say that a is divided by b. Okay, so or I can write that as b divides a. B divides a and a is divided by b, both are one and the same. If b divides a means there must exist one integer, say c, such that a is equal to bc. Then you can say that b divides a or a is divided by b. If no such integer exists, then I can say that b does not divides a. For example, if I consider a is equal to some integer 9 and b is equal to some integer 3, then b divides a will be equal to a is divided by b. I can write that as 9 by 3, and 9 by 3 gives you 3 itself. This is my integer, that is new integer, and I will define that as c. Now you can observe, if b divides a means I can represent that as a is equal to bc. So a is 9, b is 3 and c is 3. So 3 into 3 gives you 9. Right? So now here I can say that 3 is a divisor of 9. Right? Similarly, let us consider one more example. If a is equal to 5, b is equal to 2, then for b divides a, you have to write 2 divides 5. But we know that 2 does not divides 5. That means a is not equal to bc. So here I can say that 2 is not a divisor of 5. So if a is divided by b means, then we get or there exists a unique quotient, and I will denote that quotient as q. Also there exists a unique remainder, and I will denote that as r, where this remainder r satisfies the condition that 0 less than or equal to r less than b. Then you can say that a is the dividend and b is the divisor. right? This is how we define our divisibility. Now using this concept, let's move further. That is one of the important theorem, division algorithm. The statement of division algorithm says that given any two integers or just given integers, say a and b, and they have mentioned the condition that is b is greater than 0, then there exists a unique integers say q and r satisfying a is equal to bq plus r, where this remainder r satisfies the condition that is 0 is less than or equal to r less than b, where your q and r are quotient and remainder respectively. This is the statement of your division algorithm. What they are trying to tell us, given integers a and b with b greater than 0, if this is the situation, then there must exist a unique integer say q and r satisfying the condition a is equal to bq plus r, where r is in between 0 and b and your q is nothing but quotient and r is nothing but remainder, right? This is the thing they have given. So here what all the things we have to prove? First we have to show that there exist unique integers say q and r, right? Then one more part we supposed to prove is it satisfies the condition a is equal to bq plus r, right? So let's prove this theorem. First I will consider, let q be the largest integer. Okay, so since this is the, if q is the largest integer, then this will be less than or equal to a by b. I repeat, in the statement they have given that there exists unique integer and it is satisfying a is equal to bq plus r condition. That means first we have to prove that the existence of a remainder and quotient, then we have to prove that the existed quotient and remainder are unique, right? For that first we are considering that some q, this is the largest integer, so I can write that as q will be less than or equal to a divides b, right? It may be the largest integer but it will not exceed the a divided by b condition, right? So now I can write this as q is less than or equal to a by b, and this will be less than q plus 1. Q plus 1 means for this there is an increment, so obviously this will be less than q plus 1. Now multiply b throughout this inequality, so you will be getting bq less than or equal to a less than b into q plus 1. You can rewrite this as bq less than or equal to a less than bq plus b, right? Now let's do some more simplification for this. I will just subtract throughout this inequality by bq. If you subtract the inequality, you will be getting bq minus bq less than or equal to a minus bq, and this is less than b. Okay, so now bq minus bq is nothing but 0. This will be b. Why? Because bq minus bq is 0. So here you will be getting 0 is less than or equal to a minus bq, and this is less than b. Now consider R is equal to A minus BQ. If you consider R is equal to A minus BQ, then what will happen to this inequality? This will become 0 less than or equal to R less than B. Right? Now they have mentioned that A is equal to BQ plus R. From this I can say that there exists Q as well as R, but we have to prove that Q and R are unique, right? Now in order to prove Q and R as unique, I will consider two more integers, say Q dash and R dash, and I will prove that Q is equal to Q dash and R is equal to R dash, which in turn prove that Q is unique and R is unique. Okay, if Q is not equal to Q dash, then I can't say that Q is unique. If Q is equal to Q dash, then I can say that Q is unique. So that's why I'm considering two more integers, say Q dash and R dash. Okay, so now let us consider Q dash, R and R dash are the integers such that A is equal to BQ plus R. I will call this as equation number 1, and A is equal to BQ dash plus R dash. This is my equation number 2. For this, the condition is 0 less than or equal to R less than B, and for this 0 less than or equal to R dash and less than B. Right? First assume that Q is greater than or equal to Q dash. If this is the condition, let's see what happens to my proof. Okay, from equation 1 and 2, we can write that BQ plus R is equal to BQ dash plus R dash. Why? Because in the LHS side, in both the equation we have A itself. So I can write BQ plus R is equal to BQ dash plus R dash. So grouping the terms, we will be getting BQ minus BQ dash is equal to R dash minus R. So this is B into Q minus Q dash, which is equal to R dash minus R. Right? So this implies R dash minus R will be greater than or equal to 0. Why? Because we have chosen that Q is greater than or equal to Q dash. That means Q minus Q dash will be greater than or equal to 0. So I can write my R dash minus R is greater than or equal to 0. But from the given condition, that is from 0 less than or equal to R dash less than B, we have R dash is less than B. Also we have R is less than B. So this two, from these two, we will get R dash minus R will be less than B. Right? Suppose Q is greater than Q dash, this implies you that Q minus Q dash will be greater than or equal to 1. How I am writing this? Because we have assumed that Q is greater than or equal to Q dash. From this we can write Q minus Q dash is greater than or equal to 0. Right? If I am choosing only Q minus Q dash is greater than 0, I can write this as Q minus Q dash is greater than or equal to 1. Right? This is how we can write Q minus Q dash is greater than or equal to 1. So now to this, operate B on both sides. We are operating integer B on both sides. So we will be getting B into Q minus Q dash, which is greater than or equal to B. Since B into Q minus Q dash is equal to R dash minus R, from this I can say that this implies R dash minus R is also greater than or equal to B. But this is contradiction to the condition that r dash is less than b and r is less than b, that is r dash minus r is less than b. That means the assumption which we have made is wrong. Don't consider this assumption. This assumption is wrong because we are getting this step from this, right? So this assumption is wrong. We were having two cases. One is q minus q dash is equal to 0 and another one is q minus q dash is greater than 0. Here I have taken this case. For this case we are getting contradiction. That means q minus q dash is equal to 0 is true. Therefore, from this I can write q is equal to q dash, which implies r is equal to r dash. That means I can say that q is unique, also r is unique. This is how we prove the division algorithm theorem. So be careful about the statement. In the statement they have mentioned that given any two integers, say a and b, with b greater than 0, there exist unique integers, say q and r, which satisfies this condition. So first I have to prove that there exist two integers, that is quotient and remainder when we have two integers. Then I have to prove that the existed integers, which is q and r, are unique, right? So for that we have done all these steps. Let us check some example regarding your division algorithm. So we have to find out the quotient q and remainder r for the problem 207 is divided by 15. Okay, so you can easily do this. You will be getting, I can represent 207 as 15 into 13 plus 12. You can do using normal division, right? So that means here q is nothing but 13 and r is nothing but 12. So this is your quotient and this is your remainder. Now let's see one more example which is a little different. Minus 23 is divided by 5, right? So I can represent minus 23 as 5 into minus 4 plus minus 3, right? What is this? This is minus 20, plus into minus is minus 3, so we will be getting minus 23. That means in this q is equal to minus 4 and r is equal to minus 3. I am comparing this with a is equal to bq plus r. So we are getting the value of q as well as r. But in this problem, the problem creates a little difficulty or little confusion because the value of r is minus 3. We know that r cannot be negative. Why? Because we have a condition 0 is less than or equal to r less than b, right? So I cannot say that minus 3 is my remainder and q is my quotient. So I can represent this in another way, that is minus 23 is equal to 5 into minus 5 plus 2. 5 into minus 5 is nothing but minus 25. Minus 25 plus 2 is nothing but minus 23. So here quotient is minus 5 and remainder is 2. Practically speaking, and with respect to this equation, q value is minus 4 and r value is minus 3. Fine, you can say that. But along with this equation, my r should satisfy this condition. But in this case R is not satisfying this condition, so this is not correct. We will solve this using different form, right? Let's prove one more theorem which is very simple using division algorithm. Let the statement of the theorem is, let B be any integer and it is greater than or equal to 2. Okay. Suppose b plus 1 integers are randomly selected. We are selecting b plus 1 integers randomly. Okay. Prove that the difference of two of them is divisible by b. So the statement says that we are considering one integer b and it is greater than or equal to 2. Suppose b plus 1 integers are randomly selected. Prove that the difference of two of them is divisible by b. This is what they have given. So first what I will do is, I will consider q is my quotient and r is remainder when a is divided by b. Using division algorithm, I can write that as a is equal to bq plus r, where r is in between 0 and b. If b plus 1 integers yields b plus 1 remainder, if I consider b plus 1 integers, then obviously it yields b plus 1 remainder, right? But there are only b possible remainders. You can observe here, we have only b possible remainders. If that is the case, then you might have studied in your discrete mathematics, that is pigeonhole principle. Using pigeonhole principle, I can say that two of the remainders must be equal. That means b plus 1 as well as b should be equal. What does your pigeonhole principle says? If I consider m pigeons, if m pigeons are assigned to n pigeonholes, where if m pigeons are assigned to n pigeonholes where m is greater than n, then at least two pigeons occupy the same pigeonholes. This is the statement of your pigeonhole principle, right? Using this here, I can say that two remainders are equal. Because we have b plus 1 integers. If b plus 1 integers yields b plus 1 remainder, means from division algorithm we have only b remainders, right? So if that is the case, then I can say that two of the integers, or there are only b possible remainders. That means two of the remainders must be equal. So let us consider x and y as two integers, and this is corresponding to bq1 plus r and y is equal to bq2 plus r, right? q1 and q2 are your quotient. We have to prove difference between these two should be divisible by b. So difference means I have to consider x minus y. X minus y will be bq1 plus r minus bq2 plus r. I can write this as BQ1 minus BQ2, and your RR gets cancelled here. So this is nothing but B into Q1 minus Q2, which is equal to X minus Y. From this you can say that difference of two of them is divisible by B. That is, you can write this as B is equal to X minus Y by Q1 minus Q2, right? So this is how we will prove the theorem using division algorithm and pigeonhole principle rule. In the next session, I will continue with the next topic, that is Euclidean algorithm. Thank you.